On November 14, 2023, humanity's farthest messenger fell silent. After 46 years of faithfully reporting back from the darkness, Voyager 1, a machine that had become a part of our collective consciousness, suddenly started speaking gibberish. From an unimaginable distance of 15 billion miles away, the steady stream of scientific data that had redefined our place in the cosmos was replaced by a meaningless repeating pattern of ones and zeros. It was the digital equivalent of a scream, a sign of a catastrophic failure from which there seemed to be no recovery. For 5 agonizing months, the brilliant minds at NASA's Jet Propulsion Laboratory feared the worst. The legendary probe, the first human-made object to ever enter interstellar space, was now a dead machine tumbling blindly through the void. It felt like losing a pioneer, a friend who had traveled farther than any of us ever could. The team, however, refused to give up. They embarked on a rescue mission that seemed impossible, a desperate attempt to perform remote surgery on a patient so far away that every message took nearly a full day to arrive. This brush with oblivion only highlighted the profound and often baffling mysteries Voyager had already uncovered. What did this aging probe, built with technology from the 1970s, truly find at the edge of our solar system that shattered our most fundamental understanding of the universe? And what was the strange, ethereal hum it recorded from the supposed emptiness between the stars? The answers are etched in a journey of shocking discoveries, impossible odds, and the relentless curiosity of a species confined to a tiny blue dot, reaching out to touch the infinite. It all began with a cosmic alignment, so rare, so perfect, it only happens once every 155 years. In the late 1970s, the giant outer planets of our solar system, Jupiter, Saturn, Uranus, and Neptune, lined up in a celestial syzygy, creating a gravitational superhighway. This unique configuration meant a single spacecraft could visit all 4, using the gravity of each planet to slingshot itself toward the next. NASA seized this once-in-a-lifetime chance, designing 2 identical, incredibly robust probes, Voyager 1 and 2, to undertake this grand tour. What they found was a solar system far more violent, dynamic, and stranger than anyone could have possibly imagined. When Voyager 1 reached Jupiter in 1979, it didn't just see a big striped gas ball, it saw a world of unimaginable atmospheric violence, dominated by a centuries-old storm, the Great Red Spot, a hurricane so vast that 3 Earths could fit inside it. But the real shock came from its moons, which scientists had assumed would be dead, cratered balls of rock and ice. They were wrong. As imaging data for the moon Io was being processed, a navigation engineer named Linda Morabito noticed a strange umbrella-shaped plume extending off its limb. At first, she thought it was a glitch or a distortion from a star hidden behind the moon, but further analysis confirmed the unbelievable. It was a massive volcanic eruption, spewing sulfurous material hundreds of miles into space. The probe went on to capture 8 such eruptions, revealing Io to be the most volcanically active body in the entire solar system. Meanwhile, another moon, Europa, presented a different kind of mystery. 2 years later, the probes arrived at Saturn, a planet that seemed to embody a more serene, majestic beauty. But here too, Voyager revealed bizarre phenomena that defied explanation. Its famous rings, thought to be simple, uniform bands, were found to be an impossibly intricate system of thousands of individual ringlets, intricately woven and braided by the gravitational influence of tiny shepherd moons. Even stranger were the dark, radial features that appeared and disappeared within the rings, dubbed spokes, which seemed to defy the laws of orbital mechanics. And Saturn's moons were just as weird. Mimas was scarred with a massive crater, named Herschel, so disproportionately large that the impact must have nearly shattered the moon, giving it an uncanny and now famous resemblance to the Death Star. These were not just static worlds, they were dynamic, active, and filled with mysteries that we are still trying to unravel today. But it was at Saturn that the mission reached a critical fork in the road, a decision that would alter the fate of both probes and forever define their legacy. Scientists, including the influential Carl Sagan, were desperate for a closer look at Titan, Saturn's largest moon. It was the only moon in the solar system known to have a thick, dense atmosphere, one richer than Earth's. They saw it as a primordial Earth held in a deep freeze, a natural laboratory where the chemical precursors to life might be forming. Getting a close look, however, came at a steep price. The required trajectory would use Saturn's gravity to fling Voyager 1 up and out of the ecliptic plane, the flat disk where the planets orbit, putting it on a path that would make it impossible to visit Uranus and Neptune. They faced a monumental choice: continue the full grand tour, or sacrifice it for a chance to uncover the secrets of a single enigmatic moon. They chose Titan. The tension was immense as the probe made its close approach, but the gamble didn't deliver the expected payoff. Titan's atmosphere, rich in nitrogen and methane, proved to be an impenetrable smoggy orange haze. Its surface, and any potential wonders it held, remained completely hidden from Voyager's cameras. The data on its atmosphere was invaluable, but the moment was tinged with a sense of anticlimax. With that flyby, Voyager 1's planetary mission was over. It was now heading into the unknown darkness, on a path that would eventually take it out of the solar system entirely. Its departure left its twin, Voyager 2, to continue the historic journey all by itself. For the next 8 years, Voyager 2 became humanity's loneliest explorer, venturing into the deep, frozen frontiers of our solar system. It was now the only spacecraft ever sent to the two most mysterious and distant major planets, the ice giants, Uranus and Neptune. Before Voyager 2's arrival in 1986, Uranus was little more than a tiny, fuzzy, blue-green dot in even the most powerful telescopes. The anticipation was palpable. What the probe revealed was a world of serene and bizarre stillness. It was a pale, featureless aquamarine sphere, lacking the violent storms and distinct bands of Jupiter and Saturn. But its placid appearance hid a deeply strange reality. The planet is tilted on its side at an extreme 98-degree angle, meaning it essentially rolls along its orbital path. This bizarre orientation results in the most extreme seasons in the solar system, with each pole experiencing 42 consecutive years of sunlight followed by 42 years of complete darkness. Its magnetic field was an even bigger shock. It was a chaotic mess, tilted at nearly 60 degrees from its rotational axis and significantly offset from the planet's center. It was as if its north and south magnetic poles were closer to its equator. Even its moons were odd, particularly Miranda, which looked like a cosmic Frankenstein's monster, a jumbled collection of mismatched geological parts stitched together in a chaotic patchwork. 3 years later, in 1989, Voyager 2 made its final planetary encounter, the grand finale of the tour at Neptune. If Uranus was serene, Neptune was fiercely dynamic. The probe revealed a world of deep, vibrant azure, racked by supersonic winds, the fastest recorded in the solar system, reaching speeds over 1,200 miles per hour. It discovered a massive churning storm system dubbed the Great Dark Spot, reminiscent of Jupiter's famous Red One. It also found faint, dusty rings, and a host of new moons. The most fascinating was Triton, its largest moon, a world so cold that nitrogen froze solid onto its surface like snow. In a major surprise, Voyager 2 discovered that Triton was geologically active, with cryovolcanoes erupting plumes of nitrogen gas and dark dust miles into its thin atmosphere. Furthermore, it orbited Neptune backward, in a retrograde motion, suggesting it was a captured object from the Kuiper Belt. After its breathtaking flyby of Neptune, Voyager 2's grand tour was complete. It had fundamentally rewritten the textbooks, revealing the outer solar system to be a place of violent beauty and profound weirdness. Now, like its twin, its trajectory was also taking it out of the solar system, towards the great, dark unknown between the stars. The probes had left the planets behind, but their greatest and most significant discovery was still yet to come. For years they traveled toward a theoretical boundary that scientists called the heliopause, the invisible frontier, where the constant stream of charged particles from our sun, known as the solar wind, finally loses the battle against the pressure of interstellar space. Think of it as a bubble, called the heliosphere, that our sun inflates around the solar system, protecting the planets from the harsh radiation of the galaxy. All scientific models at the time predicted that this boundary would be a gentle, drawn-out affair. They expected the solar wind to gradually weaken and slowly intermingle with the interstellar medium over vast distances. What Voyager 1 found was completely, utterly different. On August 25, 2012, as it cruised more than 11 billion miles from the sun, its instruments registered a sudden, violent, and unambiguous change. The count of solar particles it was detecting dropped 1,000-fold in an instant, while the high-energy galactic cosmic rays bombarding it from the outside shot up dramatically. It hadn't been a gentle fade. It was as if the probe had punched through a wall. The heliosphere wasn't a soft, permeable bubble, but a sharp, well-defined boundary. This groundbreaking discovery revealed that our solar system is physically and magnetically separated from the rest of the galaxy, protected by a distinct shield of our sun's own making. The data was so bizarre, so contrary to every existing theory, that for months, the science team at NASA furiously debated whether it was real or just a catastrophic instrument malfunction. 6 years later, in 2018, Voyager 2 crossed the same boundary at a different location, and its instruments recorded the same sharp transition, confirming the discovery. Humanity had officially crossed into interstellar space, and the first message sent back was that we knew far less about our cosmic neighborhood than we thought. But the surprises didn't stop at the border. As Voyager 1 ventured deeper into the true void between stars, its sensitive instruments detected something that, by all rights, shouldn't be there. It wasn't a sound in the conventional sense, but a faint, persistent hum, detected in the thin plasma that populates interstellar space. Scientists eventually realized the probe was measuring the vibrations of this interstellar gas, caused by violent eruptions from our own sun. Coronal mass ejections on the sun would send out massive shockwaves of plasma that traveled outward for over a year. When these shockwaves finally reached and slammed into the denser interstellar plasma, they would make it vibrate, or hum, like a struck bell. What's truly mind-blowing is that the hum has remained remarkably stable. The probe's two long antennas, stretching out like cosmic ears, have continued to record this low, steady drone of plasma wave. Even after traveling another billion miles farther into space, the sound has stayed nearly the same. This constant hum, heard in the near-total vacuum of space, is the ambient background noise of our galactic neighborhood. For the first time in history, we weren't just looking at the space between stars, we were listening to it. By analyzing the frequency and amplitude of this hum, scientists can now directly measure the density of interstellar space, turning a theoretical number into a real, tangible measurement. It's like using sound to see in the dark. The very fact that we can hear anything at all is a testament to the incredible, almost unbelievable, resilience of these ancient machines. The Voyager probes are technological ghosts from another era, launched before the invention of the CD or the personal computer. Their main onboard computers, the Computer Command System and the Flight Data System, each have just 69 kilobytes of memory. That's not enough to store a single low-quality photo from your phone. All of their groundbreaking data, every iconic image of Jupiter's storms or Neptune's rings, was recorded on a sophisticated 8-track digital tape recorder. Their signals are broadcast by a transmitter that uses about as much power as a refrigerator light bulb. By the time that signal reaches Earth, it is so faint, less than a billionth of a watt, that it takes a global network of massive radio antennas to even detect it. It is a miracle they are still working at all. Their continued survival is owed to the sheer ingenuity and dedication of NASA's engineers, who have kept them alive through a series of clever hacks and brilliant remote fixes. In 2017, they realized the main thrusters on Voyager 1, used for orienting the probe to keep its antenna pointed at Earth, were severely degrading. Without them, the mission was over. In a stroke of genius, the engineering team decided to try firing up a set of backup trajectory correction thrusters that had been dormant since 1980, during the probe's Saturn flyby. After 37 years of cold, silent disuse, they sent the command and waited with bated breath. Incredibly, the old thrusters fired perfectly, seamlessly taking over and saving the mission. It was a testament to the quality of their original design and the brilliance of the team still watching over them. Which brings us back to that terrifying, 5-month-long silence that began in November 20. The stream of gibberish pointed to a severe problem with the Flight Data System, FDS computer's memory. The challenge was immense. The corrupted chip was 15 billion miles away, a distance so great that light itself takes 22.5 hours to cross it. A signal sent from Earth would take that long to reach Voyager 1, and another 22.5 hours would have to pass before the team could receive a response. Every single command was a 45-hour gamble into the unknown. After weeks of painstaking analysis, they pinpointed the problem. A single flipped bit on one of the memory chips had corrupted a small but critical section of the FDS software. The computer could no longer interpret its instructions correctly. The team devised an audacious plan. They couldn't repair the broken chip, so they would meticulously slice up the affected code and surgically transplant the pieces into different working sections of the computer's memory. It was the digital equivalent of performing remote brain surgery on a patient across the solar system, carefully moving essential functions from a damaged lobe to healthy ones. On April 18, 2024, after months of simulation and planning, they began sending the first commands of this delicate operation. Then they waited. The minutes turned to hours. The hours into 2 long days. Finally, on April 20th, a signal came back. It was no longer the repeating gibberish of a machine in its death throes. It was a clear, coherent readout of the health and status of the spacecraft. Against all odds, the 47-year-old probe was talking again. The cosmic scream had ended. Soon, probably within the next couple of years, the probe's decaying plutonium power sources will no longer be able to run even their most essential systems. Their signals will cease, their transmitters will go cold, and we will lose contact with them forever. But their epic journey will continue. Attached to the side of each probe is a beautiful and hopeful artifact, a golden record. It is a gold-plated copper disc, a time capsule containing sounds and images selected to portray the diversity of life and culture on Earth. Curated by a team led by Carl Sagan, it holds greetings in 55 languages, the sounds of wind, rain and surf, the song of a whale, the cry of a newborn baby, and music from Bach and Beethoven to Chuck Berry's Johnny B. Good. It is humanity's message in a bottle, cast into the cosmic ocean. After they fall silent, the Voyagers will become our ghost ships, drifting peacefully through the dark, cold interstellar void for millions of years. In about 40,000 years, Voyager 1 will pass near a star called AC plus 79388 in the constellation Ursa Minor. At around the same time, Voyager 2 will approach the star Ross 248. They will likely outlive humanity, and perhaps even the Earth itself, a silent testament to a curious, clever species that for a brief moment in cosmic time looked up at the stars and dared to reach for them. They are our legacy, a whisper of our existence echoing in the great, silent expanse.